to give the last talk today. So today I've been asked to tell you about climate and habitability on rocky exoplanets. There is an L missing there, and so I will mostly talk about exoplanets and not too much about the solar system. So to start, I have to go through this traditional slide that I really don't need to detail after 2 days of astrobiology school. But of course, when you deal with the question about habitability, you always need to start from basics and to define what's the life, how can you, what do you need for life, what's really the questions. I won't repeat that, but of course, as you know, it's not because we are chauvinistic, but just because it's not easy for us to imagine something else. We always assume that we need carbon life and with liquid water. And this is the key point, of course, as you all know. We assume that habitability is when liquid water is available, because carbon life without liquid water is not only difficult to imagine, but also probably difficult to recognize and detect. And the key point in this discussion is that we really need to detect life, and that's the objective. So when you have said that, the other question is then what do you need to get liquid water? We believe that the molecule H2O should be very abundant, at least should be abundant condensate in the outer planetary nebulas. But to get it liquid, it's actually more tricky. You need a good range of pressure below the triple point, 6.1 millibars, and at very high pressure, even if it's warm, water tends to be solid. It's the high pressure ice in the interior of icy bodies. Of course, you need to be above the freezing temperature, which is about 0 degrees Celsius, depending on the salts and other things. And you don't want to boil. And so that's a pretty narrow range compared to what you can get. And depending on the pressure, you need to be below 1 degree Celsius, a few degrees Celsius, like on Mars, for instance, in the Valley of Mars, up to 374 degrees Celsius, which is the critical point. That's a theoretical point. Maybe above that, you could imagine some chemistry with carbon molecules, but it's a little, it's a question mark. So in the solar system and probably everywhere else, most of the liquid water actually might be in the interior of icy bodies. As you all know, in the solar system, you have a very interesting place like Europa, even Ganymede and Callisto inside, and of course Enceladus, even Titan, Iris, Pluto, Triton. All these bodies are supposed to have interior liquid water oceans. And it is interesting to imagine that, in fact, most of the liquid water habitat must be like that. But of course, we know that first, it won't be easy to explore these, especially in other solar system. Even in the solar system, it won't be easy. And second, of course, even if these oceans, for instance, in Europa, may enjoy, for instance, volcanism at the bottom, silicate volcanism at the bottom, which could provide a lot of nutriments and chemical energy, still, these oceans will not benefit from something that has been absolutely crucial for the Earth and for Earth life to modify its environment. It has been the photosynthesis, of course, which has been able to, for instance, raise the level of oxygen on the Earth, and which we think is absolutely necessary to modify the environment in a significant way. But still, there is also this basic fact: if it's underground, it's not easy to detect. It's easier to detect life if it's at the surface. So within that context, you have to admit that when we talk about habitability, there are various levels of habitability, and some habitable worlds are more habitable than others. First, again, there is this quality of habitability. Active, evolve, and detectable life requires other chemical species and energy. And again, light may be a key aspect, maybe not for every kind of life, but at least for a very active life that needs energy to modify its environment. And the other point is that the duration of habitability matters, certainly. The Earth is really characterized by a very specific fact. Not only it's covered by oceans today, but it has been covered by oceans, liquid water oceans, for at least maybe 4 billion years, and that's really a striking fact. So within that context, there are various papers that deals with this. It is convenient, for instance, to use different definitions for the habitability and to use classes. For instance, in a paper by Helmut Lammer, it's a review paper already 8 years ago, you could define the fact that there is class 1 planets, which are like the Earth, benefit from permanent surface liquid water. Class 2 are maybe former class 1 planets, so maybe on which the conditions were favorable for life to start, but which has lost this ability. Because, for instance, they have lost their atmosphere, like Mars. And maybe on Mars now, we speculate that there is maybe life, but maybe most likely underground. So that's something which is intermediate between class 1 and class 2 and class 3. Class 3 being the bodies with subsurface oceans in the interior. And in the case of class 3, we will imagine that it's a good place because the life interact with the silicate mantle, like Europa and Enceladus, so you have plenty of chemical energy, for instance, and nutriments. And last, you have a class 4 in this classification, which are the bodies with a subsurface ocean between two ice layers. You have the ice layer isolating liquid water from space, and as I told you, at high pressure, liquid water tends to solidify and form high pressure ice, so you have to imagine surface ocean sandwich below 2 levels of ice, and that's probably not very good in terms of nutriments and chemical energy. In fact, in their paper, Helmut Lammer even concluded that for class 4, even if you are close enough to your star so that you have a ocean planet, if you want, ocean at the surface, if you have high pressure ice at the bottom, it's not good. In reality, there is a debate now, because even for this kind of a planet, we believe that some nutriments can go through the ice. There must be some solid convection and transporting material from the silicate mantle to the liquid water. Anyway, when we deal with astrobiology and future observations, like in the talk before, what really matters very often is the class 1, on which, I repeat, surface liquid water allows photosynthetic life, which may be able to modify its environment, and probably allows more complex life, you know, the kind of life that will build radio telescope with which we could connect. So in that context, when you wonder where you can have liquid water possible on the surface of a planet or of a satellite, a moon, well, quickly you realize that it's really a question of climate, and it's really a question of distance from the star, because really, once you talk about the surface, in most cases, it's really a question of energy that you receive, solar energy, stellar energy. If you're too close, all water, whatever you do, will be in a vapor state, and if you're too far, it will be in ice state. So that's how the habitable zone has been defined and has been used a lot. So I'm sure you've discussed that a lot already, but I wanted to say a word about that. The habitable zone is not a concept which is liked a lot. Many people criticize it or don't understand it, says it's completely stupid to assume that planets in the habitable zone are habitable. Of course, they're not. The reason is that originally the habitable zone was defined to represent that Earth enjoys, maybe in the 60s, in the 70s, at the time when the icy worlds like Europa were not well known. So it seemed natural to say, oh, we need the habitable zone to define life. But today it's still valid because, again, the habitable zone is designed to prepare observations. It's really the area where you can look for detectable life, where you have surface liquid water and life. So maybe a good way to remember that is to say the HZ, the habitable zone, is in fact the hunting zone for an astronomer. Some points which can be useful sometime. In fact, I'm going back. It will be better if we have called the habitable zone the surface liquid water zone from the beginning. The journalists and some astronomers won't be confused. The journalists will not conclude that everything is habitable. They just say, okay, it's only because it's possible to have liquid water. So that's the point. The habitable zone may be define has the region outside which it is not possible for a rocky planet to maintain liquid water on its surface. So that really means there is in some way only one habitable zone. We'll see it's a little more complex than that. That means also the habitable zone does not depend on the planet. It only depends on the star. So you should not say the moon is not in the habitable zone because it has no atmosphere. It is in the habitable zone, but of course you can be in the habitable zone and not be habitable, like the moon. So now, key question is how to characterize the habitable zone. Again, I'm repeating, having liquid water on the surface, first you have to assume that you have some water available on the world, but then it's a problem of climate and atmosphere. And so that's really what I do. It's really the science we do in our lab and many other teams around the world. It's when you have to define and imagine, speculate about the possible climate on a given planet. We've learned a lot in the solar system and we've learned a lot by modeling. And now I can summarize what we understand by this little graph. It's the idea that climate on a planet really depends on stellar insolation, of course. It will depend on the atmospheric composition and the surface volatile inventory, in other words, the amount of water, and of the rotation. Rotation is significant because it's really determine the transport, the atmospheric motions and the transport of energy, and also the obliquity, for instance, controls the distribution of insolation on the surface. So you can see that in many cases, we know about the insolation because we know about the star, we know about the orbit when we detect a given planet. So we have an idea about the zoo of possible case we have for insolation and even for rotation, we think. But the key question is the atmospheric composition. I'll come back to that. It's true that we don't know much yet about what you can find on terrestrial planets, but we know about the solar system. The thing is that once you assume this, we believe that using climate models, it's not too difficult to estimate the possible climate. And then, if you can, for instance, assume that you have some water available, you can explore the possibility of surface habitability of planets using this scheme. So, to explore the possible climate on extrasolar planets, you have various models that have been used in the literature, and you have to be careful when you read different papers. It depends really on the kind of the tool they use. There are some limits, of course. The first kind of tools that are used are 1D global relative convective models. They are still used a lot to define the classical habitable zone. The historical paper by Jim Casting in '93, and all the team, casting team, like all the work by Ravi Kaparapu. And of course, it's still very useful to explore the possible climates depending on the atmosphere and so on. There are some papers using 2D energy balance models. They still have their limitations. You also have a lot of paper using theoretical 3D, what we call general circulation model, but which are not used really to define the climate. There are many papers in which such models are really fluid dynamics models. They are used to explore and analyze the possible atmospheric circulation regime, but they are not really used to understand what the temperature is, if there is liquid water. And finally, more and more, various teams around the world, including ours, that's what I put here, are using full global climate models, which are very ambitious models designed to simulate all the aspects of the climate using universal equations. And they have been very successful in the solar system to simulate Venus, Mars, Titan, Pluto, even a giant planet now. And we've learned that they can be kind of reliable to, again, on the basis of universal equations, assuming what I told you before, to estimate the conditions on the planet. So on this basis, it has been possible to explore the range of possibilities that allow surface liquid water and possibly life. So to continue my discussion, I will, for instance, explore how do you define the inner edge of the habitable zone. If you take the Earth or any planet with oceans on the surface, liquid water, you find that if you move the Earth toward the sun to explore what is the limit of the limit of the inner edge of the habitable zone, you find that you reach quickly a limit because there is a very strong possible feedback that control that. If you increase the solar flux, temperature increase, you increase the evaporation of the ocean, you have more water vapor in the atmosphere, you increase the greenhouse effect, and this is a strong positive feedback. As a result, if you move the Earth by a few %, for instance, or any planet with liquid ocean on the surface, you find that the oceans will vaporize if you move it by only a few %. Here is the output from one of the reference 1D model from Ravi Koparapu. This is a typical casting team kind of graph. This is the relative solar luminosity. So you have to read it that way. You imagine here you're farther away from the sun, and here you're going closer to the sun. And this is the surface temperature that you can estimate at equilibrium. What you find is that the Earth is here, receive the luminosity of the Earth. If you move the planet a little bit to the right, in other words, to the top, I mean, in other words, toward the sun, very quickly, you warm the system, and at some point you start to vaporize the oceans. You have so much, assuming you have one Earth ocean, you have so much water vapor in the atmosphere, the greenhouse effect is so strong that the only solution is to radiate the surface energy in the near infrared, and you need to have a surface temperature up to almost 2000 K. So, of course, there is no more water. There are lots of details that I called, lots of points I call detail. The fact that before that, maybe you will lose the oceans through escape to space because you will have so much water vapor in the atmosphere, and especially the upper atmosphere, but I won't have too much time about that. What I can mention is the fact that in the past years, we have been able to extend this kind of studies by using 3D global climate models. We expected to get very different results than with 1D model. It's a little tricky to do because you have to realistically represent all the processes that affect a planet like that. So water vapor becomes the dominant gases. The surface pressure is affected by the condensation and sublimation of water vapor. It's a lot of fun, actually. But we were expecting the clouds that are neglected in 1D models to actually raise the albedo and in some way protect and extend the habitable zone. But that didn't work at all. The clouds tend to form high. There are lots of clouds, and they tend to have a strong greenhouse effect. But however, this was compensated by the fact that, unlike in 1D model, you discover that in such a planet, for instance, like here, you have unsaturated regions where you don't have that much water vapor, and that allows the planet to cool compared to 1D model. So in the end, we find a runaway limit, which is very close to the 1D model. And here, I just want to illustrate the fact that this is the output from, you imagine, an ocean planet. You have lots of humidity, but you find in the tropical regions, it's unsaturated, so you can radiate a lot of energy, and that really makes a difference. So anyway, we find the runaway limit at 0.95 AU around a Sun-like planet. And again, I stress on the fact that it does not depend too much on the assumed atmosphere. That's, however, is assuming an ocean and planet on which you have ocean covering the land, or at least partial ocean planet like the Earth, where ocean is connected. So even on the day side, you always have water. But if you think about it, and that has been studied by a few papers, if you think about it, if you have less water in your inventory, water will tend to accumulate in the cold trap, a little bit like Titan. On Titan, for instance, you don't have water, but you have a hydrological cycle with methane. And on Titan, all the lakes and the seas that you have are in the polar regions where it's colder. So you could imagine what we will call the Dune-like planet, if you have read or seen the story of Dune, the book by Frank Herbert. So it's a Dune-like planet. It's used in the literature, this word. And if you have little water on the planet, it will be desert, but you will have you could have liquid water at high latitudes. And you actually can demonstrate that the runaway greenhouse limit will depend on the mean insolation, not on the subsolar point, but at the edge of the polar sea, typically, if you imagine the topography allows that. So in that case, the runaway limit is extended. So now let's move to the other side of the habitable zone and the outer edge. So what is the limit? Again, you can do the same exercise. You take the Earth, you move it outside, and you imagine what happened. It's interesting because if you do that with you can't do it in reality, of course, but with a realistic climate model of the Earth, quickly you reach a limit, because when you decrease the solar flux, the temperature is decreased, you have more and more ice and snow, this raises the albedo, and this tends to decrease the temperature. And I want to illustrate that to you with a simple simulation. This is it is assuming that you take an Earth model and you move the Earth by 12%. This was done by Benjamin Charnay in our lab, who was a PhD student at the time. And if you do that, it's very simple, you find really that this runaway glaciation process, this positive feedback, is really very efficient. So I will run the simulation year after year. And what you find is that quickly, because you have decreased the insolation, you tend to increase the amount of snow and everything cool. And you start to have a lot of sea ice on the oceans. And after only a few years, so you can see here, I hope the movie goes well through Zoom, but you can see the sea ice really covering the Earth, and after only 30 years, it's nothing in terms of geology, you completely freeze the ice. If you move the Earth by 5%, it's almost the same. So as a result, at the end of this simulation, right away, the mean temperature is -60. In Australia, it's -50. So it's a very different planet, and in theory, the Earth should not be habitable. Of course, in reality, we know it's not always the case. For instance, actually this insolation, because the sun, as you know, luminosity is increasing with time, this insolation corresponds to the Earth 3 billion years ago. And we know that the Earth 3 billion years ago was habitable. It was covered with liquid ocean, actually warm oceans. So, and the reason certainly is because you had the greenhouse effect was different, and you have to take that into account. Of course, again, if you do the same simulation with the present day atmosphere, you get that. But if you add only a little bit of CO2, already, at least in our model, you can prevent sea ice to cover the planet. And if you put much more CO2 and methane, as expected on the early Earth, you can have a temperate planet. The reason, what's interesting, and what Jim Casting has always put forward, is the idea that on the Earth, the climate must have been controlled by the right greenhouse effect through the carbonite silicate cycle. I suspect that you have had already a lot of details about that in Diana Valencia talk. I repeat the idea. The concept is the idea that if you have an atmosphere with some greenhouse gas, and especially CO2, on the Earth at least, and probably when you have on many planets, you will have CO2 being weathered at the surface, being dissolved in the fresh water on the continents. It will accumulate in the oceans and will tend to form carbonates that will sedimentate and accumulate at the bottom of oceans. And on the Earth, because you have a tectonic plate tectonics, this carbonate won't stay there. They will be subducted below the continents, and at high pressure temperature, they will have metamorphosis, formation of CO2 again, and this will be released in the volcanoes. As a result, if you, for instance, freeze the planet, well, you stop this, but CO2 continue to accumulate, and you accumulate CO2 in the atmosphere, and that controls the greenhouse effect through this negative feedback. If you lower the temperature, you have a more intense water cycle, weathering, the pressure of CO2 increase, stronger greenhouse effect, and the temperature goes up again. It's a kind of a geophysical thermostat. So with that, people have been assuming, okay, the the habitable zone for the Earth, okay, I told you you should never say that, but the range of orbit on which the Earth, as we know it, will be suitable for liquid water and life will be quite large. It will be all the way up to where you can have all the way out where the CO2 greenhouse effect is sufficient to maintain surface liquid water. In reality, we now believe that you have to generalize that. It is likely that there will be many exoplanets that will be very volatile rich with a lot of CO2 and other gases, a lot of water, of course, because we have observed lots of planets more massive than the Earth. And if you just do a scale, you realize you have much more gas. You can have more volatile rich planets because of migration, like ocean planets. Many systems, you may not have early Jupiter and lots of transport of water inside and water and volatile inside the system. So you can say, okay, maybe there are lots of cases where you just have volatile rich planets with thick atmosphere, for instance. And if you imagine the Earth with a thick atmosphere, like 20 bars of CO2, and being able to maintain it, at equilibrium, the Earth would have stayed habitable without any stability in geophysical feedback. This is really questionable, of course, but the point is that it's difficult to say that it's absolutely necessary to have the carbonite silicate cycle to stabilize the climate. So now the question is, how far can greenhouse effect can keep a planet warm around a sun-like star, for instance, to start with? You can study that by first just assuming a CO2 atmosphere. And it's interesting that to realize that you cannot accumulate. It's not because you increase a huge amount of CO2, you accumulate a huge amount of CO2 that you will increase the greenhouse effect. This is the minimum flux to get 0 degrees Celsius as a function of pressure. And you can see that if you add CO2, you can go further away from the star, from the sun, but beyond 8-10 bar, the greenhouse effect does not increase anymore because the Rayleigh scattering from the thick atmosphere is actually raise the albedo in a way that is stronger than the greenhouse effect, so that there is a kind of limit which is traditionally defined in Castings' paper around 1.7 astronomical units. You can do more by adding gases like methane, but that won't change that much the effect. Or also by taking into account CO2 as clouds. We used to speculate that with CO2 as clouds, you go as far as 2.5 astronomical units from the sun, but it's not so sure, but it's kind of a theoretical limit if you want. Whatever you do with various gases and clouds, it's not easy to have any atmosphere warming the surface beyond 2.5 AU. So you can see that you can define a kind of different limits for the habitable zone, these traditional limits and the maximum possible extension, assuming clouds, for instance. One thing I want to stress is that the solar system and around every star, the habitable zone can evolve through time. I can illustrate that using the sun. Remember that the sun gets older and brighter because its density at the interior increase because of because you accumulate more helium while you are burning hydrogen, and as a result, the sun is always brighter and brighter, and that means that the habitable zone move outward, and you can see here that the solar system, what happened. Of course, Mercury never had an atmosphere probably, and have always been outside. Venus started not far from the probable limit. That's why we always speculate that it could have had an ocean early in its history, which is interesting. The Earth was inside the habitable zone, needed some greenhouse effect to start with, and in about 1 billion years from now, we'll leave the habitable zone, and it is likely that there will be some Runaway greenhouse. It will be the end of our planet. And Mars will be in the habitable zone if you had a strong greenhouse effect, but Mars did lost its atmosphere. So that's a lesson to remember, that to be habitable, of course, you need to have the right atmosphere. We all know that. There is a specific case that has been found recently. I told you, whatever you do with the greenhouse gases and clouds, it's not easy to go beyond 2.5 astronomical units. Well, there is one exception. If you assume, and it's a little, it's a real speculation, that you have an Earth-like planet, for instance, or a super-Earth, with a thick hydrogen atmosphere or hydrogen-rich atmosphere, then hydrogen at high pressure is a very good greenhouse gas that do not condense. I won't have time to detail that, but the fact is that you can extend the outer edge of the habitable zone significantly. So very quickly, I don't have much time left. My talk is a little too long, sorry. When you do it remotely, it's a little different. I will say what about other stars? As you all know, sure, in the solar neighborhood, most of the stars are actually smaller than the sun. 90% of the stars in our neighborhood, are in the galaxy, probably are smaller than the sun. And also, it's interesting because their lifetime is much longer, although they are a little brighter when they're young, so it's a problem. So what is the difference? Well, if you do the climate, you realize that when you're around the K or M dwarf star, a smaller star, you have a different Rayleigh scattering. All what I said about the Rayleigh scattering and the CO2 limit does not apply exactly the same, but it's not that different. And of course, the other big difference is that the gravitational tide tends to lock the planet in resonance, at least, so with a zero obliquity, so that the pole becomes a very strong, a very efficient cold trap. And also, it is likely that you will have a permanent night side and permanent day side. What we find, various teams, when you are locked, when you're rotating slowly, is that you tend to form lots of clouds on the day side, and that led to the discovery that this feedback, when you are in unlocked planet, dramatically expand the habitable zone of tidally locked planets. Now, if I go at the outer edge of the habitable zone, well, you find that it's not exactly the same. You have no albedo water ice feedback, and you especially have this problem of having, for instance, permanent night side. That's a problem because you can imagine that a lot of water vapor may be cold trapped on the night side, and also even the CO2 atmosphere may be cold trapped on the night side. So given that, you will find in the literature lots of graphs summarizing all that with the surface liquid water habitable zone. This is from a paper by Sarah Seeger. And I will have to conclude, but I will summarize what I wanted to say in the rest of the talk. I wanted to give you an example, to detail the example of Proxima b, which has been studied by my student Martin Turbet, and it was interesting using a lot of global climate simulations, exploring where the water accumulates, that you can find, exploring the various atmosphere you can have, in other words, the various greenhouse effects, and the various amount of liquid water. Martin was able to explore all kinds of regime, starting from a regime where you only have glaciers, to regime when you have some glacier flowing on the day side and creating lakes, and then a regime where you have lots of sea ice, but some liquid water, even if some liquid water at the subsolar point, and then you could continue the exploration. If you have enough greenhouse gas, you can have ice-free ocean. And I will conclude by saying this, summarizing what I said. And what I really want to emphasize to conclude is that the key open questions, when you want to explore habitability, if it is, for instance, likely that there are plenty of other Earths suitable for life, is that we don't know we know how to compute climate in some way, approximately. But what we don't know is what to assume for an atmosphere. It's really difficult to understand the kind of atmosphere that can be available. On the solar system, we have not enough example. If we don't have Venus, we won't dare imagining it. If we don't have Titan, we will not imagine it, I think. So we need to understand the kind of zoo we can have, because we have to understand if the Earth is exceptional or not. On the Earth, our understanding is biased. Of course, it's not a coincidence that we are on a planet which has been covered by ocean for 4 billion years. And to really make progress, I think we need observation of atmosphere. And in fact, to learn more about that, we can even learn from atmosphere well outside the habitable zone. We don't want to understand the possible zoo of atmosphere that can exist and all the processes that control atmosphere and oceans on other planets. Thank you.